Okay, thanks much for coming and for investing your time in this course. That's correct. If there are free cups, please take.
Thank you.
So, we are starting a new chapter on DFT, density functional theory, which is a workhorse of computational chemistry. But we will not do DFT today, because there are a couple of sections from Hardy-Fock and more general that we do need to cover today. So there will be, I do have plan for 4 or 5 items. So first, I will quickly go on to practical things that I was planning for yesterday, but we went over time, and I really want to offer you a pleasant and interesting homework, but without this little piece of information, it is not possible to do. So a little practical instruction. Then, we will go over refresher of the Hardy-Fock theory, and you may just, if you want to entertain yourself, feel it. And we will go over it maybe in like 10 minutes from the beginning. Just put your name, few boxes. I will collect it as a surprise quiz, but do not worry, it's more for me to assess quality of instruction rather than your abilities. And this little flowchart is important, first, so that you will remember what we did with Hardy-Fock, and second, it will be very, very similar procedure for density functional theory. They have a lot of similarities, so it will be not a waste of time. So first, practical things towards homework. Second, little refresher of DFT, and specifically focus on the observables. Observables in a narrow sense, like favorite observable of Mead is ionization energy, right? You all did it in the previous homework. You have an idea where to take it, but we will cover it with a little more detail from theoretical side. So first, practical on WASP. Second, observables in Hardy-Fock and generally. Also, I'll briefly cover background for interaction between radiation and matter. And I will give one formula, well, I will chew it for like 7 slides, but it will be one basic formula that we will use later for optical properties that we will cover later in the course after we finish DFT. So it is fundamentals. And then, after we are done with simple observables like ionization and absorption, we need to cover so-called Bloch theorem, which is fundamental for solid state. It will be a little bit more rigor to the thing that we discussed yesterday in the lab with periodic boxes and leaving a little vacuum, and how wave functions will look like. So I'm trying to put all recordings. So here are, just if you ever need them, the yesterday lab, and here are your presentations. Okay, so a little bit on. No? Yes. A little bit on the practical thing. So majority of the group here were attending free entertainment for the last 2 hours, right? Maybe you consider it differently, but I was just reviewing slides and preparing for the lecture and showing sign that yes, very good. So it's not a big deal. So practical steps that would enable some minimalistic calculations by everyone in VASP. And it would be not a problem for me to log in and show it a live way, but probably it's better just to focus. So you all were exposed to preparing 4 input files for us, right? To especially, I don't know what was more challenging, but if you look through recordings and remember your notes, you should be able to do it. And homework will be I intend to give you homework of making density of states for hydroxide, for dimer, and for perovskite thing. So we need density of states for based on VASP, right? So there is one key thing that was missed yesterday, and without which it is not possible. And some of you were already complaining. How do I transfer files if I'm logged into this supercomputer? And I have started. I went about through half of the list of the class. I've submitted applications to NERSC supercomputer so that they may have already contacted you, or they will contact and ask you to sign some forms. Did any? No? Okay. They're busy people, but they will. So if you are logged to NERSC through the chain to one computer, then to another, and then you do some successful calculations. The question is, how do you get your files back on your laptop for if it is graphical information, or if you need something more than just enjoying list of energies on the screen? Of course, you always can copy paste, but it's not the most optimal thing. So I was sitting on a photon, not sitting in physical sense, logged into the photon, created a subdirectory just to pull the dynamics, and then I checked what is the path on a photon. So the plan is that from NERSC I will send needed information to the photon, and from photon you know how to get it into your local computers. So then through this command I'm going to NERSC and checking this prompt created by London. I do not need the whole list for his files. I take only the link to project directory, and we need it because personal directories that you have very soon, they will be limited. Maybe, I don't know what is today, but something like similar to CCast, 40 megabytes or 200 megabytes, which is nothing by today. And on the project directory, there are dozen terabytes. So course, my name, and there I do see what we did yesterday in the lab, the output from VASP calculations, right? Suppose I need the outcar file, this one, and I do want it to be transferred from here to there, to photon, right? So I'm practicing standard way how we transfer files between Linux machines. Secure copy, space, file, and then user, cluster, and then I'm literally copy pasting the path where I want this thing to be copied. So this little thing is literally reproduced in here. And then I click enter, type in the password, and it's getting transferred. Make sense? No questions? You'll be able to reproduce, right? If needed.
Well, email.
Don't practice. Oh yes, please. I love emails. Especially if they are about this stuff, I will try my best answering them in the middle of the night or like at 6 a.m. If it will be something like demanding scholarship, I will pretend that I ignore them. Okay, now favorite table of Queenie and Kevin. You had a discussion on Tuesday evening, right? So if you scroll through OutCar, you will see this list of orbitals, some of which are occupied, some of which are unoccupied. For those of you who love secret commands of Linux, not secret, but just the list of orbitals start with declaration of Fermi energy, and if you type grep and then list minus after 40 lines, it will just show what is after, instead of browsing through the whole thing. So, before we go to preparing density of states, we do need a couple of pieces of information to normalize it, and the previous script with Gaussian automatically pulls it, and here it is a little more stick shift mode. So first, how to get number of orbitals? What is the number of last orbitals here? NBA doesn't stand for National Basketball Association, it's number of bands. And grep means extract line that includes this word out of this file. So you do not see because of this box, but you'll see the notes. It will tell number of bands equals 30. Same as here. Just if you do not want to browse through file and invest your visual skills on boring numbers, better reserving them for movies or whatever. Another thing you may create, it is optional. I will tell you when to wake up and focus, very concentrated. This is just a little simplification. You can create a file named input overlap and put their first orbital, last orbital, and then just number one. So then, if you were not lazy to create such file, there is a little script, extract energy pop, that will go through the outcar and extract the list of orbitals that you need to plot density of states. Right? No one forbids you to do it manually. Just go through outcar, select right list, and copy paste it in the new file. This is one of the legitimate ways, which doesn't need any commands. So I run it. I hear feedback. Does it mean someone wants to ask a question? Probably not. Okay. And then I see new file named energy pop. I do more, and it shows the same list: number of orbitals, energy of orbital, occupation. Right? Then, just because of the style of the, you have advancer and, oh, jeez. I'm not so tall to touch it by finger. We copy it into new file named states, and we can do WC, which is not water closet, it's word count. So how many lines in this file? 30, because we requested it, from the first to the last molecular orbital. And then we can grab value of Fermi energy, number of atoms, or more, who knows whether they're neutral or ionized, so it's more safer to tell number of ions. So grab number of ions, outcar tells for titanium hydroxide it was 9, right? Titanium, 4 oxygens, 4 hydrogens, and number of electrons. Grab number of electrons, outcar it tells how many electrons there are. It does skip the core electrons and count only valence. And if you were relaxing, Now, please consider to wake up. So, in the directory where you do have healthy wavecar or healthy outcar, you type this, you execute this command. So it does same thing as we had in the script you practiced in Gaussian. It will convert set of discrete levels into continuous distribution for density of states. But before it will run, it will ask silly questions to the person who is executing this command. This script was written so many years ago in a very old-fashioned, ugly style, but since then no one updated it. Therefore, instead of reading input file, it just asks from the command line. Number of states, you type 30. Minimal energy, maximal energy, you just select in which interval you need density of states from -10 to 10. Fermi, alpha plus beta, you put whatever you get from in the previous line. And then width, 0.01, same as you put in the line of arguments for script to getting DOS out of Gaussian, right? Magnitude, just one. Number of atoms in simulation 79. Number of electrons, 32. Gap of phase. I think you put here anything, just a numeric. And then it tells that the output file has been created. So DOS Fermi. Right? So this file is, again, can be either plotted with favorite software of Dicta by GNUplot, or you can download it to the local computer and plot with Excel, if you're a fan of Microsoft products.
What does magnitude mean?
Pardon?
What does magnitude mean?
Please repeat once again.
What is magnitude?
What does magnitude mean?
Magnitude.
Just put one. Put one. It is a scaling factor that will make your density of states higher or lower. Okay?
Got it.
Okay. So after you got this file, you follow the procedure that you already know. You run gnuplot space and then a script that will read this file, and you can ask, you can just open and look inside and ask Sudipto if you need to interpret. But there are similar commands. Just plot using like second and third line or whatever. And then after you run this software with this input file, with this script, it will create postdos.ps in the obsolete form. And then you convert it from PostScript from the obsolete format into modern PDF. And then we can practice once again, downloading it, SCP, this file, to the local computer, or to the photon. Right? And you put the path where you want it to be forwarded. So after this file has been forwarded to Photon, you know how to bring it to your local equipment, to a laptop or desktop. So if your laptop, like I used laptop under Mac which understands Linux commands, so I did the SCP file space period. And here how it looks like. So you remember the gap was about 3 electron volts, right? And in this version of the script, it makes field orbitals. It shows density of states also field, just graphically prompting which one is occupied valence band and which is unoccupied conduction band. So please try to practice it. I have probably sent the instructions and suggestions, but ideally it would be great if by Tuesday after the break you bring 3 density of states images for hydroxide dimer, and perovskite. Okay? Feel free to request help I really like this activity. Email me if you do not see how to do it.
So on the drug side,
Same models that you were processing with Gaussian, with Hartree-Fock, in the so many homeworks ago.
so the CSPB.
Yes.
Okay. Alright.
So the idea is that you do not rebuild models; you just use what you built before.
Okay.
Good. Okay. So a little bit on Hartree-Fock. So total energy is energy of all occupied orbitals plus energy of Coulomb repulsion and exchange stabilization. So there is a very common error for beginners in computational theory, computational chemistry theory, assuming that total energy is just energy of all occupied orbitals. No, there is also an interaction of electrons sitting on different orbitals. So there are two indices going over all occupied orbitals that should repel each other and stabilize each other due to exchange. Did anyone play Mafia?
The game?
The game?
No, but I know it.
No? At least you know what is it. A dozen people is a good number to play it, so we can play it instead of a class.
Yeah.
It's some previous like brilliant students who are a few years before they were playing, even with faculty. I don't remember why. Oh, here's why. In this game, by rules, you tell like city fall asleep, and everyone except Mafia closes eye. So if you just looking forward to relax and wake up one of the most important moments, now you can relax and fall asleep. It's not very important. So, but the Fock matrix that is being diagonalized in particle theory is expressed through four orbital two electron integrals that you know the shorthand notation. When indices are going through certain orders, they correspond to direct Coulomb or exchange. But there is a little trick that is implemented in the software. The integrals are computed in atomic basis once and forever, or at least you update until you update your ionic coordinates. And then distributions of atomic coordinates of expansion coefficients in front of atomic orbitals are stored in molecular orbitals, right? But if you if you need interactions between two molecular orbitals, there are two sets of coefficients, right? And when you multiply these two sets of coefficients in a dyadic form, dyadic is opposite to scalar product. Like if you do scalar product, you get number. If you do dyadic product, you get matrix out of vector. There is this density matrix that is composed of the products of the expansion coefficients of molecular orbitals in basis of atomic orbital. So if you are talking to a person who deals with Hartree-Fock theory, he or she uses the word density matrix in respect to this thing. All other researchers understand different thing under density matrix. So it's rather narrow, and just in case if you ever need it. And a little box covered here, there is a summation indices, and then C capital once, C capital for another time with C going over all orbitals and product of the expansion coefficients. So, a little refresher. What is going on in Hartree-Fock theory? You're probably tired and you're writing it anyway, right? So, if anyone volunteers to write it down, feel free to come up. But you're not in kindergarten and I'm not in the mood to invite you. Maybe next time when we will be doing DFT, prepare. We'll be doing this in about 3 weeks. We will be doing the same flowchart in DFT, and I will call everyone to write each portion of flowchart. So when there will be flowchart in the lecture, remember it and prepare for a little response in front of everyone. So let me examine myself. So what do we need? Well, we need that tolerance, like total energy at step I plus 1 minus total energy at step I is smaller than some tolerance limit, and then you report total energy. We start, I don't know, from position of ions, number of electrons, and I think we also, in order to start Hartree-Fock calculations, one needs to generate set of molecular orbitals or expansion coefficients. Orbital number I, ion I capital, and alpha for all atomic orbitals. Maybe different. So we need a trial wave function. Trial wave function. And then in these boxes, we should distribute the procedures that lead us to total energy. So total energy is 1 electron energy, like Hamiltonian, plus this summation with 2 indices, I, J lowercase, that was on the previous slides, right? So Coulombic repulsion minus the exchange, right? Something like this. So the protocol for total energy, where these things are matrix elements, bless you, of the electron interaction and the 1 electron attraction to ions and kinetic energy. So in order to do so, we need to, those are matrix elements. Matrix elements. And this is shorthand notation. More generally, this all is expectation value of multi-electron Hamiltonian as a bracket of the Slater determinant on the left and right. So in between, one needs to form Slater determinant. And here one needs to find determinant of the Fock matrix. Fock matrix over Webb matrix unknown energy equals 0. So this is equation that will give eigenenergies of molecular orbitals and molecular orbitals themselves. Except I and the molecular orbitals. And the step here we use either our random number, arbitrary molecular orbitals, or if you go through the loop, we use molecular orbitals from previous run. We need to formulate Fock orbital, Fock matrix in the as a mean field of influence of the electrons that do occupy occupied orbitals. Okay, let's check whether I was studying well my own subject. So what is here? Fock matrix of molecular orbitals. Guess of molecular orbitals. Positions, tolerance, limit, ions. This is good. Okay, probably I went too far. This one would be sufficient. Yes?
So, Hartree Frog and all its outputs, everything that we've learned so far, even with program or stuff on the computers, all to me is their descriptors. And are we going to get to a point where it's going to produce some sort of bigger output?
What do you mean bigger output?
Yeah. So.
What is your definition of bigger output?
Well, so it seems like all this information I could use for a descriptor. I mean, the way my advisor has his work deals with descriptors, and then you use them to, let's say, create a model, right?
Mm-hmm.
So I'm curious because everything that we've learned and dealt with, I can get these descriptors, and then do you create anything further with them? Or
No. In this course, you will never go further with them. From the bird's eye of chem informatics, this course is individual, elementary structure to property relation. It is a black box where you put in structure and get out generated descriptors or properties. But a general correlations between structure and properties is not my problem. It's not problem of this course.
Yeah.
Okay. So no bigger things in your sense. Only practical way to get how you tell descriptors out of structure. Good. Like if they are not available from experiment or from the literature, and you finally need to generate them, you do these calculations.
So this is just one way of getting descriptors.
Yes.
My understanding. Okay.
Very
Yeah.
good.
So,
Yes. Okay. And one can even probably simplify it. So if you if a stranger catches you in the store and asks what Hartree Fock, procedure is you may mention that one needs guess molecular orbitals, one needs Fock matrix, one need to diagonalize Fock matrix and check energy conversion. And in between, one does need the way of finding total energy out of these C coefficients, right? Okay, I'm going to collect, put your names.
maybe it was easy for you.
It's much.
That's his.
I see the name. So no one does pure Hartree Fock productive calculations these days. So you do not need to do things like this in real papers. But if you do DFT, a little more detailization and knowledge would be helpful. So just prepare for the similar style of flow chart when we go to the stuff. Wrong device. Basically the same, right? And then one can report total energy, or if this theory is run by Mead, he needs more than just total energy. He needs descriptors, observables, right? So, what are? I will probably postpone the ionization and affinity to later, but one of the descriptors for everyone who stands near the windows and was attending the meeting, one of the descriptors is oscillator strength, right? And oscillator strength is a way to characterize ability of specific piece of matter to interact with electromagnetic radiation, right? So electromagnetic radiation is like infinite wave of electric field strength E, this red stuff, and magnetic field B, this blue stuff, that oscillate in space and in time and propagates. It is when I'm irradiating by this lamp, it's like plane waves are approaching me. Plane waves of electric and magnetic field. And for some of you, the equation for plane wave is in form of exponential becomes favorite formula, right? We already started it yesterday, and we will do it again today. So electric field. Now, if we do have a molecule, a polymer, some piece of matter, then, and we forget magnetic field because it is boring, the electric field will affect on all electrons, which are charges, and nucleus, which are also charges, and may do something to a molecule, right? So, since molecules consist of charges, it's natural to assume that there will be interaction between light and matter. Okay? Catch me if you can in lack of logic. So, it's not the whole thing, but in the simplest approximation, Hamiltonian, and like if we do theoretical science, we need always to speak about Hamiltonian, which is operator of energy. So, energy of interaction between light and matter is H0, which is Hamiltonian of molecule itself, minus dipole term. So dipole times electric field. And you know what dipoles are, right? It's like positive and negative charge offset, selected by distance, and in static electric field, it just aligns along field, right? So this is good for molecules interacting with light as well. So what, yeah, this one, positive, negative distance, times field times dipole. What is dipole for a molecule in the microscopic sense? You know what dipole is for two charges, but molecule is more than two charges. Even simplest hydrogen molecule is two positive nuclei and two negative electrons, right? Each of them has charges, and each of them can be specified by positions. So this fat symbol means there is a vector above. Some lazy people, Nathan, close your ears. So, assume that you close. Some lazy people from physics like to skip vector sign and put fat symbols instead of vectors. So you same as here. So positive with charge number in front of vector, make vector summation of all positive, minus vector summation of all negative. So it is a dipole corresponding to a molecule, right? Dipole operator. Of course, now it is operator if it is true molecule with these orbitals. It will be like closed distribution, but one can always find expectation value of this operator. So it is what one should put into Hamiltonian. And do not fall asleep. It is needed for descriptors. You know this equation that you like all the time. If you do have operator and if you do have wave functions, you can always find either expectation value or matrix element of transition. Right? So let's assume that we do have occupied orbital, let's say number 2, and unoccupied orbital, let's say number 3. For each orbital there is a like wave function. Well, there is wave function of overall system before and after excitation. And due to interaction with light, I'm skipping important details. So, what happens if you shine light on sensitive people, sensitive molecules?
They get energized. They absorb energy. Right?
They're getting excited.
Excited.
So exciting means electrons are getting promoted from occupied orbitals to unoccupied. Good? Excited, promote electron from OC to un-OC. Make sense? And one may formulate wave function of the multi-electron wave function of overall molecule before and after this promotion happens. So in order to assess whether this transition is possible, one does need, one may want to put Hamiltonian of light to matter interaction in between initial and final and see whether it is something substantial or zero, right? So it will be descriptor of ability of a molecule to absorb light. As a big secret specifically to meet, I will say that oscillator strength is a square of this matrix element.
Oscillator strength is
Square of this matrix element. So, we are going to practice plugging the dipole matrix element for initial Slater determinant for ground and final Slater determinant when electron from orbital 2 is promoted to orbital 3. And we are going to check how it will look like. Feel free to look on it with one eye. It is not, it is not critically important, but it will later we will return to this material again and again. And why do I bother you with this boring information? What is my motivation? What is your motivation to listen to this? What is the benefit? I'm not going to do long intrigue and tell answer right away. So, formally, anything that happens with molecule, all descriptors depend on multi-electron properties. Right? And finding matrix elements between Slater determinants is a big pain in part of the body. Everyone has different parts where one experiences pain. But specifically for this matrix element of light to matter interaction in linear dipole approximation, there will be a wonder. If you do not do multi-electron calculations every day, like Nathan either doing now or will be mandated to do so by his advisor, you don't care. But if you do, you recognize how heavy, hard, and adverse it is. So it's like many lines of derivations. But for linear absorption, all multi-electron calculations will reduce just to matrix element in terms of one electron orbitals. So everything except orbitals involved directly in excitation will be cancelled out. And I'm going to show this wonder. But if you are like bored about details, you can just take this message. And later on, very soon, both in lecture and in the practical labs, we will use this fact. So linear absorption can be cast in form of one electron orbitals matrix elements. And it is not a fantasy or approximation, it is literal. It is like a rigorous thing. Okay, so if we have two electrons and two orbitals, I'm slightly oversimplifying. Orbital 1, orbital 2, electron 1, electron 2. We forget about nuclei because they will be cancelled out anyway. So just dipole element, add together positions of electrons, first electron and second one. And we need to find matrix element of this operator in terms of wave functions like this. If we do excite, and we are doing Hartley products instead of Slater determinants, but if with Slater determinants results will be the same. I just respect my own laziness and your time. So Hartley product. If it is excited state, when electron number 2 was promoted from orbital number 2 to orbital number 3, then it is Hartley product. First electron resides in the orbital number 1, but second electron will jump to electron number 3. Okay. This is our operator. So, matrix element of dipole operator between ground G and excited E. As approximation, instead of Slater determinants, we use Hartley products. So, ground, excited. Ground is first electron in first, second electron in second. Excited, it's not usable here. First electron in first, second electron in third. And the angular brackets, when we do Bryant-Cat, are corresponding to integration over position of first and second electron, right? No objections. So we are going just from Dirac notation to regular integration. So matrix element of dipole operator between ground and excited is integration over position of first electron and position of second electron. And then instead of bra, we put with little stars. First electron in first orbital, second electron in second orbital. Here we just reduce the operator. And then for the cat, first electron in first orbital, second electron in the third orbital. So the goal and expected benefit is that the equation will be reduced without any tricks to expression that will include only one integral instead of two. And right now we are doing two integrals to represent like many electron systems. So instead of n integrals in general case, it will be only one. Here we just use n equals 2 to have it to fit into one slide. Okay. So, which question would I ask to Mary if she will be here? Well, to all of you, but which question is natural to ask right now? So, we have product of three factors. First factor bra, last factor cat, and inside there is operator that consists of two terms. 1 times summation of two terms times another factor. What will be the number of terms in the result? 1 times 2 times 1. Right? So first term when we will keep only R1, second one when we will keep only R2. But the rest of expression will stay the same, both integrals, right? And if we would have like 10 or 100 electrons, it will be 10 or 100 terms. And we all believe that we are using good orbitals, which are orthogonal. So with R1, it will be first electron, first orbital, second orbital, second orbital, first and first, second and third, integration over R1. And for and second term will be the same, but here will be R2, position of the second electron. Okay? Two terms. One for position of first electron, second for position of second electron. So how do we, and then we can use the principle of ancient Romans. If you are falling asleep, it is the right thing to do. It's the most boring part. I will speak not loud. So principle of ancient Romans, divide and conquer. So you divide this expression on two terms and process one by one. So here we have integration over position of first electron. So it means it will affect this one, and this one, right? And then we take integration over position of second electron. It will affect this part and this one. So we can rearrange the factors here. For example, we can pull everything that depends on R1 into here, into there, and into there, right? And everything that depends on R2 can be moved here and there. Those who are watching, do you follow the, is logical, right? Because, good. So the integration over R2 doesn't affect functions on R1. And then we will have product of two integrals over R1 and over R2. The integral over R1 will include three factors, right? Two wave functions and one operator, two orbitals and one operator. The second one will include only two factors, two orbitals, right? And similar thing will be for the second part. Now, I am looking only on the first, no? Here on the second, okay, I can look at the second term. First in the first, second in the second, first in the first, second in the third. Integration over R2, split on two products. First, product, here things that depend on R1 will be first in the first. And here from this side, we see once again, first in the first, right? You do see. Star, no star. So according to normalization, orthonormality, it will be 1. And we get rid of this integral. And if it will be more than two independent electrons, they also will get rid due to orthogonality. And the second term has a product of second electron in second orbital, position of electron 2, and then second electron in third orbital, right? So integration over position of second electron. So first term disappears, and this one is something that those who took introductory quantum theory, where all problems are considered only for one electron in different potentials, it will be most appetizing and favorite thing. So you have just one electron orbital, another one electron orbital, and position operator between them, right? So in order to describe multi-electron excitation processes, we just need to find matrix element of position operator in basis of molecular orbitals. which is so much simple compared to from where we started, from many electron multiple degrees of freedom, impossible for modern computers. But here, this is something really easy. That one doesn't need. If you have molecular orbitals, this procedure can be done on a laptop or even on a cell phone, right? But it is, in some sense, rigorous, right? We didn't neglect any multi-electron properties. Once again, two terms, first and second, for first and second electron. In each of them, the product of orbitals will be processed based on orthogonality, and note that in one term it become one, in another it will be just cancel, and another term will be just a matrix element of the position operator between two orbitals, which are involved in event of optical absorption. So this is needed to find descriptor of this transition dipole matrix element. Good. And here's the same thing, just in Dirac notation. From ground to excited equals just matrix element of position between three orbitals. Okay. Now, do you recognize this little image? Does it remind you anything from our meeting yesterday in the lab? Yes. So we do have model, and just as an example, I put model that consists of two atoms, but we can, of course, much bigger. And then there is a concept of periodicity, which means that if it is a solid, then the same pattern of atoms is reproduced in the next box, and in the next box, and in the next box. So boxes are offset from each other by lattice vector. You can call them by letter A, right? And this periodicity may happen in all three directions, X, Y, and Z. So position of ion 1, ion 2. And then in the, okay, if you're deciding to sleep or not to sleep, now it is time not to sleep. So if we do have next image of the unit cell, then those atoms for which Cartesian positions were R1 and R2, here will be vector addition, R1 plus A vector, R2 plus A vector. Translation. Each atom translated by A. If it will be next replica, it will be R1 plus 2A, R2 plus 2A. Okay? Translation. Good. So minimal configuration that repeats is a unit cell. If the configuration is repeated, then potential how electrons are attracted by nucleus will be repeated by the same pattern. So if you shift position in space by n times of the lattice vector, you get the same interaction with nucleus. Right? So shifting from one unit cell to another one doesn't change attraction of electrons to nucleus. So suppose that we have maybe unit cell with one atom, and then we do have it shifted by 1, 2, and 3. So the red thing would correspond to the potential. Suppose that we solve equations in our head, or if you have powerful computers that solve everything for us, how would the electronic wave function look like? if the so potentials will be attractive near the ion and like zero in between. If ions are close enough to each other, one may expect that there will be some portion of electronic wave function at each atom, right? It's not a big surprise, not a big approximation. And the question is, since all atoms in each replica, in each image of the unit cell are identical, have the atoms of the same element, will be there any difference between portion of electronic wave function localized on one and another atom? Will they be also identical or slightly different? So what is opinion of Sudipta?
It should be the same.
Huh?
It should be the same.
Should be the same?
Identical.
Identical. Any other opinion? Anyone signed up or took in the past solid state physics? Okay. If you are going to deal with nanostructures, you may want to sign up for this course when it is offered. So, Ben and Gage are not here, but they were. I saw them taking introductory quantum theory. So, when you are translating, when you consider wave function at different points of space, there is a natural property of wave function. In addition to change of its like absolute value, it always accumulates phase, right? So if a wave packet is moving, it accumulates this phase. If even static plane wave, it is just pure accumulation of phase, right? This expression of e to the power I kx is accumulation of phase that we were drawing as a spiral. So the idea that is referred to Felix Bloch and named as a theorem after him is that these little portions of the wave function that Sudipta assumed equivalent, they will be equivalent in the absolute value, but they will differ by factors. So each time as you go from unit cell to unit cell, it will accumulate additional phase, which means it will, if you plot charge density or probability, it will be the same, but it will be different phase. It will kind of rotate in okay? And the theorem by Felix Bloch is that the wave function at unit cell number n at position r plus n times lattice vector will be the same as in the source unit cell times exponential with some momentum times offset in space, number of unit cells and lattice vector. So the further the replica is, the larger phase accumulation is. So the part that is not changed is referred to like atomic portion of the wave function. And in addition to this, there is a plane wave that corresponds to accumulation of the phase. And this plane wave is critically important if you have periodic solids, because as we will see later, there are eigenstates even for ground state of a matter that will correspond to overall orbital or wave function moving with constant velocity or constant momentum. And in order to describe it, we need this plane wave factor for all wave functions in periodic space. So do not memorize or take notes right now if you are not in a good mood, but we will come back to it, and it makes connection to the k-points file. Okay? Like if we set up this k equals 0, then it will become a point that we practiced last time. But as soon as we consider something periodic, there will be momentum. Okay, so kind of done with boring things, and now coming to a little easier things that we would likely like. Simple descriptors. So I'm walking in circles. We were starting from total energy is matrix element of Hamiltonian between Bryant-Ket oscillator determinant, which is heavy multi-electron stuff. And it includes both eigenenergies of orbitals and Coulomb exchange. Now, let's assume I will be getting crazy on the next few slides. I will be like a lamp that is about to burn out. I will be flashing and then quenching. So for a minute, let's assume that we do not have this Coulomb exchange. The total energy is only summation of eigenenergies of occupied molecular orbitals, right? It is not right, but we'll do it as an approximation for simplicity, and then we will see what we neglect. So this is a wrong expression which we just practice for simplicity. So system that includes n capital electrons is summation of all energies of occupied electrons. So now the next natural question will be, what would be the energy of a system that has been ionized if we remove one electron? What would change in this equation?
Wouldn't the electron go up on the orbital, so the energy would increase?
So let me. I think it will be shown in a few slides, but like if you do have orbitals and there are electrons, and then we ionize, which means we remove one electron.
Oh, well,
Right?
there are two. I have a question there because we're getting the thing energy. It's excited. I thought we said it would go up to the next orbital.
No. There are different things.
Okay.
There. Not many different things, but few. Let's consider four different things. I'll try to not get to more than four. So, 4 electronic configurations of the same molecule, same system. First, ground state neutral. Number of electrons is equal to charge of the nuclei. So then ionized when we remove one electron, or in chemical chemists will say oxidized, maybe removing an electron. Would it be okay?
I don't know why you're looking at me. I'm not.
You are the most chemical chemist in this audience. Huh? You are you have the strongest background in chemistry in this audience.
That might be true.
So oxidized or
But I
whatever,
specifically
ionized.
your group.
Well, I took my last chemistry class in high school. Since then, so there are many wonders in chemistry for me. So ionized, removing one electron. Then reduced when you intentionally add electron, And the fourth one, when you keep the same number of electrons, but you promote electron from occupied to unoccupied. Those are different. When you excite, you keep the same number of electrons. And when you ionize, you remove electrons. Okay? So what will be the energy if you remove an electron? How would this formula change?
It would go down. One's
It
reduced.
will go down, but sure. But what should we do to this equation?
Well, it's reduced. If it's a summation of the total energy, there's less total energy than it's combined.
I'll tell you anecdote about people like drinkers of alcohol. In specific areas, sometimes drinks are sold in half gallon or half liter. So one drinker asks another one, what would be 0.5 plus 0.5? I feel my instinct that it will be 1 liter of drink, but I cannot express it mathematically. So I know that your instinct is right, energy will be less, but by how many?
N-1.
Yes, Anas is the champion.
Okay.
So we should put -1 here, right? So energy of last orbital will be not contributed. -1 Anas +1 as a credit. Okay, and if you do affinity, then you do just +1. Right? So in previous year, Christian was making it as a presentation on like about Gaussian, and I stole his slide because I really like it. So we have occupied orbitals, right? If we remove electron from highest occupied, the total energy will be less by the energy of this orbital. If we add another electron to lowest unoccupied, the energy will be more by energy of this orbital. And if we excite from HOMO to LUMA, the total energy will change by their offset, right? No objections.
So, one more time.
Oh, sure, with pleasure. I'm saying it one more time each year when I'm allowed to teach this course. So here are the orbitals.
Yep.
Here are the electrons.
Yep.
If we ionize, if you remove an electron, total energy will be less by the energy of this orbital, because we remove electron from there.
Yep.
If we reduce, if we add electron, it will be more by energy of this orbital.
Yep.
And if we excite, do lowest excitation from occupied to unoccupied, total energy will change by the offset between HOMO and LUMA. Yes? So for neutral, you have 2 electrons on HOMO. For singly ionized, you have 1 electron on HOMO. You remove it and take its energy away. If you have reduced, you put electron here, so you add energy of LUMA. Right? So 3 configurations. Neutral. How can we tell if it is singly ionized? Right, word starts same like animal with whiskers.
Cation?
Yes, cation. And if you put one more, anion. Neutral, cation, anion. So in your top portion of your summation, you have an electron, it's credit of Ns. If you have cation, it will be n-1. If it will be anion, it will be +1. Okay. And here, if you still do not believe me, here is deadly convincing proof. So if we hate summation symbols, then we can just add together. So energy of neutral species is equal to energy of first orbital, energy of second orbital, then up to energy of orbital number n. Right? If it is cation, then at this position we have 0, and we end our summation at n minus 1. If you have an anion, then at the next position we have energy of orbital n plus 1. So the formal definition of energy of ionization that one should practice any time is possible and without any approximations is to subtract total energy of the cation minus total energy of neutral. So subtract this one minus this one. Then this one cancel, this one cancel, this one cancel, this one doesn't cancel. And it comes with negative E sub n, right? So if you do neglect direct Coulomb and exchange, then energy of ionization is equal to energy of HOMO. If you do see, if you compute ionization energy once literally by definition, and another time just by assessing energy of HOMO, and you see they are in discrepancy, you approximately see the level how much multi-electronic effects are important for this molecule, right? Same if you need energy of ionization. You subtract energy of anion minus energy of neutral. And then there are blue lines to cancel. This cancel, this cancel, this cancel, this cancel, this stays. So energy of orbital n plus 1 will be electron affinity, EA. IE, ionization energy, EA, electron affinity. Probably it will be homework in in 3 weeks to do all this stuff for all your molecules. Good. I think it should be enough, right? Thank you for your patience. Thank you for your appreciation.
I still have more questions.
Please, please.
I don't, it's specifically to what I was asked you earlier, so after class.
Okay, so everyone is free to depart. Have a pleasant break. I hope the homework will make it more pleasant. And looking forward to see you on Tuesday after the break to see both you and the homeworks.
Next week. Okay.